Lesson one of the rotational physics for CP Physics due to the coronavirus, all online. If you're looking for these videos, they're in the Coach Botzer YouTube page under the Corona Rotation playlist. And what we're looking here when we're talking about rotational motion is if we think back to what we've done this year, everything we've done this year has been what's referred to as linear motion. We've looked at stuff going to the right and going to the left. We've looked at stuff going up. We've looked at stuff going down. And that's it. That's what we've done. What we haven't looked at yet is how does physics apply to things that are moving in a circle? How does physics work to things that are spinning around left and right? If I'm driving a car and I turn it, how does the physics apply to that? Because we haven't looked at this yet. This is a complete mystery to us. It is a complete unknown. So that's what we're going to start looking at here. In short, we're going to be looking at every single topic we did this year. We're going to be looking at kinematics, so displacements, velocities, accelerations. We're going to be looking at forces again, like F equals ma. We're going to be looking at conservation of momentum with P equals mv. We're going to be looking at energy, mgh and 1/2 mv squared. But every time we do this now, we're going to be thinking about it in a rotational way. And I'll often say it's a rotational analog. It's just we're thinking about things spinning now rather than just moving back and forth. Okay? Now, in doing this, we actually need to define some new terms in the world of physics. Previously in the year, whenever we went through things for linear motion, everything we've already done here, we have quantities like displacement, which is how far from a start and finish point are you? We have a velocity, which is how fast you're moving in a direction. An acceleration, how quickly you're changing your velocity. Time, mass, force, and momentum. These were all things we had earlier in the year. When we're looking at rotational motion, we're going to have slightly different words to describe some of these things. Because, for displacement earlier on in the year, whenever we did this, I could say I started here and I ended here. This is my displacement. That's delta x. Well, we talked about if we ran in a circle, you start and end at the same position, so your displacement is 0. But that doesn't mean you haven't traveled at all. You still have traveled. You physically went around the track, right? You did all that. So how are we going to think about things from an angular standpoint? And how can we think about things from a rotational or looking at loops you've kind of gone through? So we have some different words for these things. For displacement, we actually call this an angular displacement. Okay? So it's still a displacement, but it's an angular displacement. It's how much of an angle you've gone through. For our velocity, we have, and this is getting clever, an angular velocity. And if you want to play a guessing game, you can probably guess what our acceleration is going to be. It's an angular acceleration. Ta-da! Nothing too crazy there. Time. You may want to say we're going to get an angular time, but that doesn't make any sense. You've never had a watch on your hand that says an angular time. It's just counting seconds. So time is still time. Nothing happens there. For mass, we may want to think about the mass can't change either. If time is time, mass is mass. And mass is mass, but when we think about mass in physics, one of the parameters we think about is how easy or difficult it is to get that mass to begin to accelerate. And if we think back to a great equation we had earlier in the year, which was F equals ma, Newton's second law, we knew that if we had a larger and larger mass, if this mass went up and the force stayed the same, the acceleration would have to go down here. Now, in a rotating way, this mass, what we're thinking about, isn't a mass, but we're thinking about how difficult it is to rotate an object. And if you just, and this is going to be weird if I stand up here, but if you stand up and you hold your arms out and rotate just side to side like this, you could do that. If you go to pull your arms in, you notice that as you're standing, it's easier to rotate. Like if you stand up and do this, you're like, woo, I'm doing it. And when you do this, you can rotate a lot faster. That's why you see gymnasts and like figure skaters, they tuck their arms in to spin. This is a ease or difficulty in rotating, which is not a mass, but it's a different quantity. And this quantity is a moment of inertia. Okay, so it's a little different than what we've previously talked about with mass, but going back to that F equals ma idea with mass is something that you're trying to move, this is a moment of inertia. For force, if any of you work on cars, this would be called a torque. We've talked about this a little bit in class throughout the different units, so some of you are kind of familiar with this. And lastly, but not least, momentum goes back to the classical angular momentum. Okay. Now, we have a bunch of symbols for all of this stuff, and this is what we're going to concern ourselves with here. And our symbols are a bunch of Greek letters that are a little bit tricky to write if you're doing them for the first time. There's a Trinity Blue. But for angular displacement, we're going to use a theta for an angle. For angular velocity, we're going to use an omega. For angular acceleration, this is an alpha. Some people call that the Jesus fish. Time is still time. It's a t. Moment of inertia is going to be a capital I. Torque is going to be a tau, and it is a vector, so it has an arrow. And angular momentum is either going to be a lowercase l or it could be a capital L. Lowercase l is normally whenever you only have like one object moving, and capital L is the entire bulk of the system there. Okay, so this is how we're turning all of our old linear motion quantities into angular quantities, objects that are kind of rotating or moving in a circle. Now, because of this, there's actually been a bunch of equations that we've had this year that need to get rewritten. If you look at this here, equations 1, 2, 3, 4, and 5 actually look very similar to what we did all the way back with catapults, whenever a number of students were shooting marbles throughout the room. These were all the equations on that half sheet of paper I gave you. F equals ma, that's a classic one. Here's our work equation that we briefly saw doing roller coasters. Here's an energy equation from coasters. Here's momentum from our momentum games, an impulse from our games and rockets, and then a conservation of momentum from the games as well. So yeah, all of this stuff like we have done. Everything over here, you have seen this equation at some point in the year, whether it was board games or something else. And some of you might have actually encountered some of these other topics along the way. I know whenever we did bridges, I was talking about torques. I know there was a group that was doing angular momentum for their game because they had a person that they were hitting and it was rotating. These are all things that have come up like bits and pieces throughout the year. We're just finally tying it all back together. Well, what we're going to do here is we're going to look at our equations that we have, like v equals xt. Velocity or speed equals a displacement or a distance divided by time. And we're going to look at all these equations, and we're just going to put in the new symbols that match up with the old one. So if we take a look at this here, we've got velocity equals a displacement divided by a time. Well, for us now, this is a angular velocity, and it's equal to an angular displacement divided by a time. So it's the same equation, we're just putting in the angular quantities instead of the original ones. And we're just going to do this for every single one going through. I'll put them in different colors so that they're easy to see. An acceleration is now an alpha, and that's equal to a change in velocity divided by a time. And that means that we can say this is equal to, oops, I don't want a v there, I want an omega, excuse me. This is equal to a final angular minus an initial angular, all divided by a time. For equation 3, we have a final angular velocity is equal to an initial angular velocity plus the acceleration multiplied by a time. These are all vectors. And then my favorite equation, displacement equals vt plus 1/2 at squared. This is just going to become theta equals the initial angular velocity times time plus 1/2 alpha t squared. That's a half there. And we just keep doing this all the way down for all these equations. This one is omega final squared equals omega initial squared plus 2 alpha theta. Things only start to get weird when we start looking at forces. When we look at forces, things get a little hocus pocus because forces are becoming torques. And 2r, are the velocities supposed to have vectors? Ooh, great question, and yes, they are. I missed that. Whoop, whoop. Technically, and this is just me, technically these thetas are vectors too. They're a direction. I typically don't write that symbol in because, oops, I just deleted that. Because whenever I do this, I am writing these in as I'm already thinking about the direction of something rotating one way and maybe an acceleration happening the other way. But technically, these are also vectors here. I just typically don't write it because I'm lazy, and it's kind of assumed like you're rotating in one direction. So, but technically they're vectors. You can rotate clockwise or counterclockwise, or for any of my European British friends out there, anti-clockwise, because that's how they talk. But yeah, thanks for the question. In terms of forces, though, remember, we don't have forces in rotation. We have torques. And because we have these torques, things drastically change up. We do still have the F equals ma equation, just we can rewrite it as torque equals I alpha. That's totally good and valid because the mass has been replaced by moment of inertia, and the acceleration is now this angular acceleration, which we'll talk about. But we can actually also write this, if you remember back when I was pushing doors early in the year, we can write this as R cross F, which is also the same thing as saying R times F times the sine of theta. Okay? And this right here, we've briefly talked about a cross product in class, or rather we talked about the dot product in class. This is a new way of multiplying things in a special way. We will talk about this. Torque is a very important thing for us. That's a very important equation there. Okay? But it does look a little different. We'll get to it. Interesting enough, if we go to work, work is still work. It's just still a W. But now, instead of a force by a displacement, we're going to have a torque multiplied, and rather dotted, with some angular vector, some displacement vector. Kinetic energy looks kind of the same, but kinetic energy here, instead of being 1/2 mv squared, it's going to be 1/2, and then the m is going to become an I, the moment of inertia, and then the v is going to become an angular velocity squared. Remember, energies in work, they're not vectors, so they don't have vector symbols over them. They're just quantities. They're scalars, so they don't have a direction. Luckily for us, because of this, work is still just equal to the change in kinetic energy. So that from coasters doesn't change at all. Okay, nothing's changed there. Let's see, let's pick another color. Let's go orange. For momentum, this becomes an angular momentum, which we can write as an L. And this is just going to equal I, the moment of inertia, times omega. For our impulse, Ft equals the change of omega. This is going to look weird, but this is a torque multiplied by a time is equal to a change of angular momentum. And that's basically saying if you have an object that you are caught, like putting a rotating force on, and you do that for some amount of time, it's going to continue spinning faster and faster, and that gives it more angular momentum because we have more of an angular velocity. And last but not least, we can't forget about it, the sum of the momentums initially equal the final momentum. We could say that the sum of the angular momentums, all of them, just equal, and the sum of all the little bits and pieces can be the total thing, this big L at the end. That's equivalent ways of writing that. Essentially, the big thing is that the initials equal the finals. Okay? And this is every equation that we will be using and we have technically learned this year, but now they are all in rotational ways of doing them. So they all look a little different, but that is everything we've learned. We're just now rotating. We're just spinning with it. So nothing's different about that.